Assalamualaikum warahmatullahi wabarakatuh and a very good day to our lecturer, Encik Zul Afiq bin Sazali. We are from Group 9 from Section 5. Today, we will be presenting our program-based learning assignment for engineering mathematics. My name is Muhammad Waki bin Kamruzaman and together with my team members, and we will analyzing two interesting engineering case studies. For our introduction, this project analyzes the rotation of an automatic robotic arm and the full flow dynamics of a rocket engine. We will determine the robotics arm angular velocity and calculate the engine's rapid increase in full consumption using differentiate techniques. Our mathematical results are interpreted using computer-generated equations and Desmos graph. Ultimately, calculating this exit rate of change provides essential data to improve feedback control system and prevent mechanical or engine failures. Looking at our cases, case 9.1 involves a robotic arm in automated manufacturing that rotates according to a program motion function. Finding its angular velocity ensures it operates safely within mechanical limits. Case 9.2 looks at aerospace engineering, where we must calculate the rate of change or acceleration of fuel flow delivered to a rocket engine to prevent structural stress during a mission. To solve both real-world problems, the primary mathematical method we use is the product rule because both functions consist of two sub-functions multiplied together. We will also apply standard trigonometry, exponential, and power derivative rules. I will now pass the presentation to Samsul to show our digital solutions for the first case.
Thank you, Waki. Let's dive into case 9.1, the robotic arm movement system. To find the angular velocity, we must calculate the first derivative of the displacement function, theta t equal to 4t sin t. First, we define our subfunction. Let u equal to 40, which give a derivative of 4. And then let v equal to sin t, which give a derivative of cos t. We then apply the product rule formula. Substituting our value into the product rule, we get omega t equal to 40 times cos t plus sin t times 4. This gives us our final angular velocity equation, omega t equal to 40 cos t plus 4 sin t. Interpreting this rotational behavior, if omega t is positive, the arm rotates counterclockwise. If negative, it rotates clockwise. If it equals 0, the arm is instantaneously at rest. So this is tangent line graph for case 9.1. On this slide, we verify our solution using a Desmos graph. The graph displays the oscillating movement of the robotic arm. As you can see, the gradient of the tangent line exactly matches our calculated derivative at that specific instant, proving our manual calculation are correct. So now I will pass the floor to Faris Irfan.
Thank you, Samsul. I will continue for our presentation. So in this case 9.2, we must find the rate of change of the rocket engine flow given by Ft equals to T power of 3 E, e power of 0.02 T. So we must differentiate the component first. uh, let u equals to t power of 3 and the derivative is 3 t power of 2. For v, it is equal to e power of 0.02 t. So we can apply the chain rule to get the 0.02 e power of 0.02 t. And the next one, we must assemble this back into the product rule formula. So to simplify the expression, we factor out the common terms resulting on the equation on the left side. To find the acceleration of the fluid flow at exactly t equals to 20 seconds, We substitute the 20 into the equation. Breaking down the calculation, we multiply them, and this gives us the final rate of 2028.885 liters per second square. On this slide, we use the decimals for our verification of the solution. So the graph shows a steep nonlinear and increase in fluid flow. So the positive gradient of the line exactly at t equals to 20 confirm our calculation that the fluid delivery is accelerating very rapidly. I will now hand it over to our next member to our next presentation. Thank you.
So thank you Faris for the explanation. To bring everything together, let's look at our final answer and interpretation. For case 9.1, our final formula is omega t equals to 40 cos t plus 4 sin t. Successfully allows engineer to calculate the exact instantaneous rotational speed of the robotic arm at any given second, knowing its direction based on whether the value is positive or negative. For case 9.2, our final calculation proved that 20 seconds the rocket fuel flows is increasing at a massive rate of 2028.85 liters per second square. What do these findings means for engineering? First, for system control, knowing the exact angular velocity allows the robotic arms feedback system to ensure precise and smooth manufacturing. Second, for safety and stability, identifying the rapid flow increase of over 2,000 liters per second square allows aerospace engineer to make a vital adjustment, preventing engine instability or catastrophic failure. Finally, through the digital verification, we successfully proved that our manual calculus matched the digital graphing software perfectly. That brings us to the end of our PBL presentation. On behalf of Group 9, thank you very much for your time and attention. Assalamualaikum warahmatullahi wabarakatuh.